Deep beneath the frozen landscapes of Greenland and Antarctica, hidden layers of ice hold secrets older than human civilization itself. These ancient frozen records, known as ice cores, are like time machines, capturing snapshots of Earth's past in delicate layers of snow that fell thousands of years ago. Picture this: every winter, a fresh blanket of snow settles, trapping tiny air bubbles, dust from distant deserts, and even ash from long-forgotten volcanic eruptions. Over millennia, these layers compress into ice, preserving a detailed diary of our planet's history. And today, scientists can drill down into these icy depths, extracting cylinders of ice that reveal astonishing clues about prehistoric climates, catastrophic events, and even the air our ancestors breathed. What makes these ice cores so extraordinary? Imagine holding a piece of ice formed during the last ice age, and within it, discovering microscopic traces of storms that raged across continents, or evidence of sudden temperature shifts that reshaped entire ecosystems. These frozen archives don't just tell stories, they rewrite them. For example, ice cores have revealed that Earth's climate can change dramatically in just a few decades, a discovery that reshaped how we understand our planet's fragility. They've uncovered traces of volcanic eruptions so massive they blocked out the sun for years, triggering famines and upheavals in ancient civilizations. And perhaps most hauntingly, they've preserved air bubbles containing the exact mix of gases from a time before industrialization, offering a stark comparison to today's atmosphere. But how do researchers decode these frozen messages? It's a painstaking process, combining cutting-edge technology with the patience of a detective piecing together clues from a crime scene millions of years old. From analyzing the chemistry of trapped air to measuring the dust layers that reveal ancient wind patterns, every detail in an ice core is a puzzle waiting to be solved. And the revelations don't stop there. These icy time capsules are helping us predict future climate shifts, understand the triggers behind mass extinctions, and even shed light on how human activity is altering the planet. So join us as we journey into the heart of these frozen archives, where every layer of ice holds a story, and every discovery challenges what we thought we knew about Earth's past and its future. To pull Earth's history from these frozen layers, scientists rely on a fascinating blend of chemistry, physics, and detective work. Each ice core is a vertical timeline, with the deepest sections representing the oldest snow, some dating back over 800,000 years. The key to unlocking these records lies in the subtle clues hidden within the ice. Take oxygen isotopes, for example. The ratio of heavier to lighter oxygen atoms trapped in the ice acts like a prehistoric thermometer, revealing temperature fluctuations with striking precision. A higher proportion of heavy oxygen might indicate a warmer period, while a shift toward lighter isotopes often points to an ice age. But temperature is just the beginning. Those tiny air bubbles trapped between ice crystals, they're literal time capsules preserving samples of ancient atmospheres. By analyzing the mix of carbon dioxide, methane, and other gases, researchers can track how Earth's air has changed over millennia. One of the most startling discoveries came from comparing these bubbles to modern air. Pre-industrial levels of carbon dioxide never exceeded 280 parts per million. Today, that number has skyrocketed, a direct result of human activity etched into the ice like a warning from the past. Then there's the dust, layers of fine particles carried by winds from distant deserts or volcanic eruptions. paint a picture of ancient weather patterns and catastrophic events. A thick band of ash might correspond to a massive volcanic explosion that darkened skies and altered climates worldwide. Traces of lead or sulfur can even reveal the rise and fall of early metalworking civilizations. It's as if the ice keeps a receipt for every major disturbance in Earth's system, whether from natural disasters or human influence. What sets ice cores apart from other climate records, like tree rings or sediment layers, is their incredible resolution and global reach. While a tree might document annual changes in a single region, an ice core from Antarctica or Greenland captures planetary shifts, droughts in Africa, monsoons in Asia, or industrial pollution from continents away. And because ice sheets form so slowly, their layers remain undisturbed for ages, offering a clarity that other geological archives can't match. The process of extracting and studying these cores is anything but simple. Teams brave sub-zero temperatures to drill thousands of meters down, carefully retrieving cylinders of ice that must then be transported and stored at freezing conditions to prevent melting. Back in labs, lasers and mass spectrometers measure isotopes, while gases are extracted under vacuum conditions to avoid contamination. Every step demands precision, because a single mishandled sample could erase centuries of data. Yet the payoff is immense. Ice cores have rewritten textbooks proving that climate can shift abruptly, not just over millennia, but within a human lifetime. They've exposed the delicate balance of our atmosphere and given us a front-row seat to Earth's ever-changing story. And perhaps most importantly, they've turned ancient ice into a mirror, reflecting both where we've been and where we might be headed. One of the most groundbreaking revelations from ice core research is just how wildly Earth's climate has swung between extremes over the millennia. Those delicate layers of ancient ice tell a story of a planet that's far more dynamic than we once imagined. Hidden within the frozen chemistry are unmistakable signs of past ice ages periods when glaciers swallowed continents, and sudden warming spikes that reshaped ecosystems in the geologic blink of an eye. Take Greenland's ice cores, for example. By measuring oxygen isotopes trapped in the ice, scientists discovered that temperatures during the last ice age plummeted to around 10 degrees Celsius colder than today. That might not sound like much, but on a planetary scale, it was enough to turn fertile landscapes into frozen tundra and drop sea levels so low that land bridges emerged between continents. What's even more astonishing is how abruptly these changes could occur. Ice cores from both Greenland and Antarctica capture evidence of climate shifts happening within decades, not the slow, gradual transitions we once assumed governed Earth's past. But here's where things get truly fascinating. While ice cores prove that rapid climate fluctuations are part of Earth's natural rhythm, there's a crucial difference between then and now. Those ancient temperature swings were triggered by natural forces, shifts in Earth's orbit, volcanic eruptions, or changes in ocean currents. Today's warming, however, is accelerating at an unprecedented rate, driven overwhelmingly by human activity. The ice doesn't lie. Pre-industrial levels of greenhouse gases remained relatively stable for thousands of years, but the last century's spike in carbon dioxide dwarfs anything seen in the ice core record. This isn't just academic curiosity. Understanding these ancient climate patterns helps scientists separate natural variability from human influence, fine-tuning models that predict future warming. Ice cores have become a benchmark, showing us what Earth's climate looks like when left to its own devices, and how dramatically we've disrupted that balance. They've also revealed surprising resilience in the planet's systems, along with terrifying vulnerabilities. For instance, certain thresholds once crossed could trigger runaway effects like melting permafrost releasing even more greenhouse gases. Perhaps the most humbling lesson from these frozen archives is that Earth's climate has never been static. It's a system in constant flux, capable of both nurturing life and upending it. The difference this time, for the first time in history, one species holds the power to influence that system on a global scale. And thanks to ice cores, we have a front row seat to the consequences. While ice cores reveal Earth's climate rhythms, they also preserve dramatic evidence of catastrophic events that reshaped the planet, none more striking than the fingerprints of ancient volcanic eruptions. Hidden within those frozen layers are thin bands of ash and spikes in sulfuric acid, silent witnesses to explosions so powerful they darkened skies across continents. These aren't just geological footnotes, they're apocalyptic chapters in Earth's story, etched into the ice with chilling clarity. One of the most startling examples comes from Antarctica, where a spike in sulfur compounds marks the eruption of Mount Toba around 74,000 years ago. This wasn't just any volcanic event. Toba unleashed enough ash and gas to block sunlight for years, plunging the planet into a volcanic winter that may have decimated early human populations. Genetic studies suggest our ancestors faced a near-extinction event around this time, a bottleneck that ice cores help explain. But Toba is just one entry in ice's volcanic ledger. Deeper layers reveal other colossal eruptions, like the unknown volcano that erupted around 540 AD. Its sulfuric acid signature so pronounced it appears in ice cores from both poles. Historical records from Europe and Asia describe years of cold summers, failed harvests, and strange red sunsets, eyewitness accounts that align perfectly with the ice's chemical record. Even more recent eruptions, like Indonesia's Tambora in 1815, left their mark. That explosion triggered the infamous year without a summer, when snow fell in June and crops withered worldwide. Ice cores confirmed Tambora's sulfur cloud circled the globe, a stark reminder of how local disasters can ripple across oceans and generations. What makes these volcanic records so valuable isn't just their scale, it's their aftermath. By studying how ecosystems and human societies recovered or collapsed after these events, scientists uncover patterns that could inform modern disaster response. For instance, ice cores show that eruptions injecting sulfur into the stratosphere have the most devastating climate effects as the particles linger for years, reflecting sunlight away from Earth. This insight helps prioritize monitoring of active volcanoes with similar potential, like Alaska's Pavlov or Italy's Campi Flegrei. Meanwhile, traces of lead pollution in ice layers after major eruptions hint at how ancient civilizations adapted or failed to. In some cases, volcanic winters sparked migrations or technological innovations. In others, they accelerated the fall of empires. Perhaps the most sobering lesson from these icy archives is how interconnected our world has always been. A volcano erupting in Indonesia can freeze rivers in Germany, just as industrial pollution from one continent now leaves its mark on Antarctic ice. The difference today is that while volcanoes are forces of nature, humanity has become a geological force in its own right, capable of altering climates as dramatically as any eruption. Ice cores don't just preserve the past, they hold up a mirror showing us the profound power of natural events and the even greater responsibility we now bear. Those microscopic air bubbles locked in ancient ice are more than just frozen curiosities, they're direct samples of the very air our prehistoric ancestors breathed. Each one is a tiny, pristine vault, preserving the exact chemical makeup of Earth's atmosphere from hundreds of thousands of years ago. When scientists crack open these bubbles using specialized vacuum chambers, they're essentially inhaling the same air that swirled around woolly mammoths or early human hunter-gatherers. And what they've found rewrites everything we thought we knew about our planet's atmospheric history. The most striking revelation: carbon dioxide levels have always danced in lockstep with global temperatures. During ice ages, when glaciers stretched as far as the eye could see, CO2 concentrations hovered around a mere 180 parts per million. But when warmer interglacial periods arrived, those numbers climbed to 280, a natural rhythm that held steady for nearly 1,000,000 years. That is, until the last century. Modern measurements show CO2 levels surging past 420 parts per million, a spike so abrupt it looks like a seismograph needle during an earthquake when plotted on ice core graphs. What makes this discovery so unsettling is the sheer speed of today's change. Past rises in CO2 unfolded over millennia, giving ecosystems time to adapt. The current increase, by contrast, has happened in little more than 100 years, a geologic blink of an eye. Even more telling, the ice cores prove today's CO2 levels are higher than at any point in the last 800,000 years, with no natural explanation like volcanic activity or orbital shifts to account for it. The culprit is unmistakable: human industry. But here's where the ice cores offer both a warning and a strange kind of hope. They show that when CO2 rises, temperatures follow, a relationship so consistent it's practically a law of nature. That means today's emissions are effectively loading the climate dice, stacking the deck for more extreme warming. Yet these frozen records also reveal Earth's resilience. After past warming events, the planet eventually rebalanced, pulling CO2 back down through natural processes like ocean absorption and plant growth. The difference now is whether human actions will allow those slow restorative forces to catch up, or if we'll keep outpacing them. Perhaps the most humbling lesson from these ancient air bubbles is how radically we've altered an atmospheric recipe that remained stable for millennia. They're silent witnesses to a truth we can no longer ignore. For the first time in Earth's history, one species holds the power to rewrite the planet's atmospheric script, not over eons but within a single lifetime. And just as the ice faithfully recorded that change, future cores will preserve our response. Between those layers of pristine ice, hidden beneath the shimmering clarity, lies something unexpected: dust. Not just random particles, but vast deposits of fine sand and silt carried across continents by ancient winds. These aren't mere impurities, they're the footprints of forgotten storms, the echoes of droughts that reshaped civilizations. When scientists examine these dust bands under microscopes, they're essentially reading the diaries of prehistoric weather systems, written in grains of desert sand that once darkened the skies for generations. Take the Sahara, for example. Today it's the world's largest hot desert, but ice cores from Greenland thousands of miles away reveal periods when Saharan dust fell like snow on the Arctic. How, during especially arid eras, stronger winds lofted unimaginable quantities of dust high into the atmosphere, where global air currents carried it poleward. One particularly thick dust layer in Greenland's ice, dating back around 4,200 years, coincides with the collapse of the Akkadian Empire in Mesopotamia. Historical records describe crop failures and mass migrations, a societal collapse that ice cores now link to a centuries-long megadrought, its severity etched into the ice as clearly as words on a page. But dust tells more than just disaster stories. Subtle variations in particle size and composition act like ancient wind vanes, revealing which directions prevailing winds blew during different climatic eras. Larger grains, which fall out of the air quickly, point to nearby sources, while fine dust suggests epic journeys across oceans. By mapping these patterns, researchers have reconstructed atmospheric circulation from eras when no human recorded the weather. For instance, ice cores show that during the last ice age, winds were far stronger and more turbulent, carrying dust from Asia all the way to Antarctica, a testament to how dramatically Earth's weather systems can transform. Perhaps most intriguing are the connections between dust and human history. Layers enriched with copper or lead often align with the rise of metalworking cultures, their mines and smelters spewing particles caught by winds and frozen in time. Other spikes in dust correlate with agricultural expansions when plowing exposed soils to erosion. There's even evidence that prolonged dusty periods may have pushed early humans out of Africa, as arid conditions made survival untenable. It's a humbling thought. The same winds that shaped our ancestors' migrations now lie trapped in ice, waiting to whisper their stories to anyone who listens. What makes these dusty archives so powerful is their universality. A single storm's debris settling onto an ice sheet becomes a timestamp for droughts, winds, and human activity across the globe. And as modern climate change alters wind patterns and expands deserts, ice cores remind us that dust isn't just a relic of the past. It's an active player in Earth's future, capable of cooling temperatures by blocking sunlight or fertilizing oceans with minerals. The next chapter in this story is still being written, grain by grain, in the ice sheets of tomorrow. Embedded within the icy layers are clues not just of Earth's past, but of moments when the cosmos itself reached down to shape our planet's destiny. Among the most startling discoveries in ice core research are sudden spikes in exotic metals, platinum and iridium, elements so rare in Earth's crust that their presence points to one extraordinary source: asteroid impacts. These metallic fingerprints, preserved with perfect clarity in Greenland's ice, tell stories of celestial collisions powerful enough to alter global climates and rewrite the course of life itself. One particularly chilling example dates back 12,800 years ago, when a thin but unmistakable layer of platinum dust settled across the northern hemisphere. This metallic anomaly coincides precisely with the onset of the Younger Dryas, a bizarre climatic U-turn where Earth, emerging from an ice age, suddenly plunged back into freezing conditions for over 1,000 years. The timing is no coincidence. Geological records from this period reveal scorched landscapes and microscopic diamonds formed under extreme pressure, while ice cores from as far apart as Greenland and Antarctica captured the global fallout of what was likely a fragmented comet or asteroid strike. The consequences were catastrophic. Iconic megafauna like woolly mammoths and saber-toothed cats vanished abruptly, their disappearance etched into the fossil record alongside evidence of wildfires spanning continents. Early human cultures, including the advanced Clovis people of North America, saw their tool-making traditions disappear almost overnight, a cultural extinction preserved in ice alongside the platinum that may have triggered it. What makes these cosmic signatures so valuable is their precision. Unlike gradual climate shifts, asteroid impacts leave behind a stark before and after divide in the ice, a single layer separating one world from another. Scientists have even matched these metallic spikes to known impact craters, like the 31-kilometer-wide Hiawatha, a crater hidden beneath Greenland's ice sheet, which dates suspiciously close to the Younger Dryas event. The implications are staggering. Celestial events we often relegate to dinosaur eras may have played recurring roles in shaping human prehistory, but the real power of these discoveries lies in their warning. Ice cores reveal that while asteroid strikes are rare, their environmental effects, global cooling from debris blocking sunlight, acid rain from vaporized rock, and wildfires from superheated re-entry fragments mirror threats we now face from human-caused climate change. The difference, unlike prehistoric societies, we can see these dangers coming. By studying how past life weathered cosmic winters, we gain survival strategies for planetary challenges ahead. Those metallic traces in the ice aren't just relics of disasters, they're guideposts, showing how fragile our world can be when the universe decides to throw a stone. Tucked between those frozen layers, alongside dust and air bubbles, lies another silent witness to Earth's fiery past: microscopic flecks of charcoal. These blackened fragments, almost invisible to the naked eye, tell a story of landscapes consumed by flames, of forests that burned not decades or centuries ago, but millennia. When scientists sift through ice core samples, these charcoal particles act like tiny smoke signals from prehistoric wildfires, revealing how often and how fiercely fire swept across the planet long before humans began keeping records. What makes these charcoal traces so revealing is their pattern. By measuring their concentration in different ice layers, researchers can map wildfire activity across time, uncovering a clear link between fire and climate. During warm, dry periods like the one we're experiencing now, charcoal levels spike dramatically. Take the early Holocene around 8,000 years ago, when ice cores show a surge in charcoal coinciding with rising global temperatures. Vast stretches of North America and Eurasia became tinderboxes, their forests ignited by lightning strikes or human activity. The ice preserves these events with eerie precision, offering a timeline of Earth's fiery heartbeat. But it's not just frequency that ice cores capture, it's scale. Certain layers contain so much charcoal that they hint at mega fires, blazes so colossal they dwarf anything in modern memory. One such layer, dating back 4,600 years in Greenland's ice, aligns with archaeological evidence of widespread burning in Siberia and North America. These weren't isolated incidents, they were continental infernos fueled by droughts that lasted generations. The chilling takeaway: today's record-breaking wildfires from Australia to California might not be anomalies, but echoes of a pattern ice cores have seen before. This ancient fire record isn't just about the past, it's a blueprint for the future. By comparing charcoal peaks with climate data from the same ice layers, scientists have pinpointed the exact temperature and humidity thresholds that turn landscapes into firestorms. Those thresholds are now being crossed with alarming regularity, as rising temperatures and shrinking water supplies recreate the conditions ice cores warn about. There's even evidence that wildfires themselves can accelerate warming, as burning forests release stored carbon, a feedback loop frozen into the ice as a cautionary tale. Perhaps most striking is how these microscopic charcoal flecks connect human history to planetary cycles. Some of the sharpest spikes in wildfire activity coincide with early agricultural expansion, when humans began clearing land with fire on a massive scale. The ice, impartial and exact, records our ancestors' first unintended experiments with climate modification and their consequences. Now, as we face a world where wildfires are growing larger and more frequent, these frozen embers remind us that fire isn't just a force of nature. It's a mirror reflecting the delicate balance between climate, ecosystems, and the choices we make. And just as the ice has preserved the ashes of the past, it's now quietly documenting the flames of our own era. Buried within the ice cores is a sobering timeline of human industry, not just from the last century, but stretching back millennia. Among the most revealing traces are heavy metals like lead, which tell a story of civilizations rising, exploiting resources, and collapsing, all recorded in icy layers with the precision of a chemist's ledger. Take the Roman Empire, for instance. Around 2,000 years ago, their vast lead smelting operations, fueled by mines in Spain and Britain, spewed so much metal into the atmosphere that Greenland's ice still bears the chemical signature. The spikes are unmistakable. Lead levels soared during Rome's peak, then plummeted as the empire fragmented, mirroring its economic decline. It's as if the ice itself kept track of ancient GDP. But Rome wasn't alone. Centuries later, medieval Europe's thirst for silver left its own toxic legacy. When scientists analyzed ice from the Alps, they found lead concentrations peaking again in the 1200s, aligning perfectly with booming silver mines in Germany and the rise of coinage-driven trade. Even more striking, the ice reveals how plagues and wars stalled industry. A sharp dip in lead around 1350 coincides with the Black Death, which wiped out so many workers that mines sat abandoned for decades. These aren't just abstract numbers, they're economic pulses frozen in time, showing how closely human prosperity and pollution have always been intertwined. Then came the Industrial Revolution, which turned the planet's atmospheric ledger upside down. Ice cores from Antarctica show lead levels surging 20-fold in the 1800s as coal-fired factories and leaded gasoline reshaped the skies. But here's the twist. While ancient pollution ebbed and flowed with civilizations, modern contamination never retreats. The ice makes it undeniable. Our pollutants don't vanish. They accumulate. What makes these records so powerful is their impartiality. Unlike historical texts, which might glorify rulers or downplay crises, ice cores don't lie. They show how the Bronze Age collapse, the fall of Rome, and even the Little Ice Age left chemical fingerprints, proof that environmental strain often walked hand in hand with societal unraveling. And now, as we drill deeper into these frozen archives, we're confronted with an uncomfortable truth. Humanity has been altering the planet on a global scale far longer than we realized. The difference today is the sheer scale and permanence of our mark. Future ice cores won't just record our industries, they'll judge how we responded to the warnings they preserved. The ice doesn't just preserve climate data, it's also a frozen ark safeguarding fragments of ancient life that once thrived in long-vanished ecosystems. Among the most astonishing discoveries hidden within these icy layers are perfectly preserved pollen grains, bacteria, and even viruses, suspended in time like biological snapshots. These microscopic time travelers offer a window into worlds we can only reconstruct, revealing how life adapted to past climates and what dangers might awaken as the ice retreats. Take pollen, for instance. Those tiny, near-indestructible shells of plant material found in ice cores act like botanical fingerprints, telling scientists exactly which trees, grasses, or flowers dominated a region thousands of years ago. A sudden shift from tree pollen to grass pollen in a layer might signal the arrival of an ice age, turning forests into tundra. Conversely, a spike in pollen diversity could mark a warming period as ecosystems flourished. But the real surprise came when researchers found viable ancient bacteria in Siberian permafrost ice microbes that had been dormant for tens of thousands of years, yet could still be revived in labs. These organisms aren't just curiosities, they're living records of evolutionary adaptations to extreme cold, holding secrets about how life persists in Earth's harshest environments. Even more startling are the viruses. In 2019, scientists extracted 15,000-year-old viruses from Tibetan glacier ice pathogens unlike anything seen today. What makes these discoveries so critical isn't just their age, but what they reveal about how viruses evolve alongside climate. As ancient ice melts, researchers fear dormant diseases could re-enter ecosystems, much like the anthrax spores released from thawing Siberian permafrost in 2016, which infected reindeer and even humans. The ice cores prove that pathogens can remain infectious after millennia in deep freeze, raising urgent questions about what other microbes might awaken as global temperatures rise. But these biological relics aren't just threats, they're also teachers. By comparing ancient viruses to modern strains, scientists can track genetic mutations across centuries, uncovering how diseases adapt to shifting environments. Pollen records, meanwhile, help predict how ecosystems might respond to today's rapid warming. If certain plants thrived during past warm periods, they could dominate future landscapes too. And those revived bacteria, some produce enzymes that work in extreme cold, offering potential breakthroughs for medicine or industrial processes. What makes these frozen time capsules so extraordinary is their duality. They're both warnings and guides, proof that life is resilient, yet vulnerable to abrupt change. As we drill deeper into the ice, we're not just uncovering Earth's past, we're reading a playbook for survival in an uncertain future. The next chapters of this story are still being written, not in ice, but in how we respond to the lessons it preserves. Beneath the frozen surface of ice cores lies an unexpected clue to Earth's oceanic heartbeat, traces of salt and minerals that map the ebb and flow of ancient ocean currents. These subtle chemical signatures, carried by winds and locked in ice for millennia, reveal how the planet's vast water highways have shifted over time, triggering climate upheavals that reshaped human history. One of the most dramatic examples, the Little Ice Age, a centuries-long chill that gripped Europe from the 14th to 19th centuries. While paintings from the era show frost fairs on the Thames and glaciers swallowing alpine villages, ice cores tell the deeper story. A slowdown in the Atlantic's mighty conveyor belt, the Gulf Stream, left its mark in plummeting salt concentrations in Greenland's ice. The science behind this is as elegant as it is revealing. When ocean currents weaken, less salty spray gets whipped into the atmosphere to eventually settle on ice sheets. By measuring sodium and chloride levels in ice layers, scientists can reconstruct current strength with surprising precision. During the Little Ice Age, these readings dropped sharply, confirming what historical records hinted. A faltering Gulf Stream diverted warmth away from Europe, turning its climate into something closer to modern-day Alaska. But here's what ice cores add to the puzzle. The change wasn't gradual. Chemical spikes show the current collapsed in fits and starts, with abrupt drops aligning with historical crises like the Great Famine of 1315, when years of cold rains rotted crops and starved millions. Yet ocean currents don't just respond to climate, they drive it. Ice cores from Antarctica tell a parallel story of the Southern Ocean's rhythms, where mineral dust from Patagonia and salt from sea ice reveal how currents there amplify or dampen global climate shifts. During the last ice age, for instance, iron-rich dust in the ice spiked whenever ocean currents shifted to upwell nutrients, fertilizing plankton blooms that sucked carbon dioxide from the air. This created a feedback loop. Cooler oceans absorbed more CO2, which further chilled the planet. Today, researchers watch these same currents with growing unease. Fresh water from melting Greenland ice could already be slowing the Atlantic's circulation, threatening to repeat the Little Ice Age's regional cooling even as the rest of the planet overheats. What makes these chemical clues so invaluable is their predictive power. By matching past current shifts to temperature records in ice cores, scientists are refining models of how ocean circulation might respond to modern climate change. The stakes couldn't be higher. A major current slowdown wouldn't just alter weather patterns, it could disrupt rainfall that feeds billions, drown coastlines as sea levels rise unevenly, and even release stored ocean heat to accelerate warming elsewhere. The ice cores offer a sobering reminder. Earth's climate isn't just shaped by the air we pollute or the forests we cut down, but by the invisible, churning forces of the deep. And as we decode their ancient rhythms, we're learning that tampering with one part of this system can send shockwaves through them all. The lesson etched into these salty layers is one of interconnectedness. A change in wind patterns off West Africa can alter currents that moderate Europe's winters, while meltwater from Antarctica can rewrite rainfall patterns as far away as India. Ice cores don't just record these connections, they warn us how delicate they are. And as we stand at the edge of another potential ocean current shift, these frozen archives remind us that the planet's past is still speaking if we're willing to listen. Hidden within the frozen layers of ice cores lies a radioactive fingerprint of the Sun's restless energy, beryllium-10. This rare isotope, formed when cosmic rays strike Earth's atmosphere, acts like a cosmic rain gauge, measuring how much radiation from deep space reaches our planet. But here's the twist: the amount of beryllium-10 trapped in ice isn't constant. It fluctuates in precise cycles, revealing the Sun's invisible shield, its magnetic field strengthening and weakening over decades. When solar activity peaks, that magnetic shield deflects more cosmic rays, leaving less beryllium-10 in the ice. During quiet periods, more rays slip through, increasing the isotope's concentration. It's as if Earth's ice sheets have been keeping a meticulous log of the Sun's moods for millennia. What makes these records so groundbreaking is how they've reshaped our understanding of solar influence on climate. For years, some argued that modern global warming could simply be the Sun growing brighter. But ice cores tell a different story. While beryllium-10 confirms the Sun's output does vary, most famously during the Maunder Minimum, a 17th-century lull in solar activity that coincided with Europe's Little Ice Age, the isotope's long-term trends don't align with today's rapid warming. In fact, over the past half-century, as temperatures soared to unprecedented levels, solar activity has remained relatively stable or even slightly declined. The ice doesn't lie. No solar cycle in the last 800,000 years matches the speed or scale of current warming, but the Sun's role isn't just about brightness. Beryllium-10 layers also expose a fascinating secondary effect: how cosmic rays might subtly influence cloud formation. Some theories suggest that when more cosmic rays penetrate the atmosphere, they seed low-lying clouds which reflect sunlight and cool the planet. Ice cores show this mechanism might have amplified past natural climate swings, like the cooling during the Maunder Minimum, when reduced solar magnetism allowed extra cosmic rays to reach Earth. Yet even here, the data is clear. Modern cloud cover changes can't explain the overwhelming warming trend. The real driver, as ice cores prove by comparing past solar cycles with greenhouse gas levels, is the unprecedented rise in human-emitted carbon dioxide. Perhaps the most compelling lesson from these radioactive traces is how they help separate natural climate drivers from human influence. By matching beryllium-10 peaks with temperature proxies in the same ice layers, scientists can calculate exactly how much the Sun contributed to past warm and cold periods, and how little it explains today's crisis. The Sun may be the ultimate power source for Earth's climate system, but ice cores reveal we've become the conductors, redirecting that energy in ways nature never intended. And as we decode these cosmic records, we're left with an undeniable truth. While the Sun's rhythms shaped our past, our choices are now shaping the future. Among the most startling patterns hidden in ice cores are sudden, dramatic spikes in methane, a potent greenhouse gas that occasionally surged in Earth's past, leaving behind chemical fingerprints of chaos. These aren't gradual increases, but explosive jumps where methane concentrations rocketed upward in the geological equivalent of a heartbeat. What makes these spikes so alarming is their sheer speed, and the clues they hold about how quickly Earth's climate can flip into a new, unstable state. Take the Younger Dryas period, for instance. Ice cores show methane levels leaping by nearly 50% in under a century, a blink of an eye in planetary terms. This wasn't just a minor fluctuation. It was the atmosphere itself rewriting the rules, with consequences that rippled across ecosystems worldwide. So where did all this methane come from? The ice cores point to two likely culprits, both tied to warming. First, vast Arctic permafrost, frozen for millennia, began thawing en masse, releasing pockets of methane trapped underground like bubbles in a soda bottle. Second, as temperatures rose, wetlands expanded across continents, their waterlogged soils becoming perfect factories for microbial methane production. This created a vicious cycle. Warming unlocked methane, which accelerated warming, which released even more methane. The terrifying part, these feedback loops didn't require thousands of years to kick in. Ice cores proved they could ignite within decades, catapulting the climate into uncharted territory. Today, scientists watch history's playbook unfolding in real time. Satellite surveys show methane concentrations rising faster than at any point in the ice core record, with plumes now bubbling up from Siberian lakes and Arctic ocean floors. Parallels are impossible to ignore. Just as prehistoric warming triggered methane releases that amplified climate shifts, today's thawing permafrost and expanding northern wetlands are priming the pump for a similar surge. There's one crucial difference, though. While ancient methane spikes were triggered by natural warming, the current rise is overwhelmingly human-caused, and we're adding fuel to the fire by directly releasing methane through agriculture, landfills, and fossil fuel leaks. Perhaps the most sobering lesson from these icy archives is how little it takes to tip the balance. Ice cores reveal that methane levels remained remarkably stable for 10,000 years until the industrial era. Now they're climbing at a rate that would make past spikes look sluggish. The message from the ice is clear. Once these feedback loops start, they're incredibly hard to stop. And unlike our ancestors who faced these changes unknowingly, we're watching the dominoes begin to fall with our eyes wide open, and the power to intervene still barely in our hands. The same ice cores that reveal Earth's climatic heartbeat also hold unexpected clues about our own story, human evolution itself. Hidden within those frozen layers are climate shifts so dramatic they pushed our ancestors to adapt, migrate, or perish, reshaping the very trajectory of civilization. One of the most striking examples comes from Africa around 70,000 years ago, when ice cores show the planet plunging into a prolonged drought. Pollen trapped in the ice tells us savannas shriveled into deserts, and dust levels spiked as lakes vanished. At precisely this time, genetic studies suggest human populations dwindled to near extinction, with perhaps just a few thousand survivors. Then, as the ice records reveal a return of wetter conditions, something remarkable happened. Those resilient bands began migrating out of Africa, their footsteps echoing across continents. It wasn't just wanderlust, it was survival, driven by climate swings preserved in the ice like pages of a forgotten diary. But the influence of climate on human destiny didn't stop there. Fast forward to the dawn of agriculture, around 12,000 years ago, and ice cores capture another pivotal shift. The end of the last ice age. Suddenly, oxygen isotopes in Greenland's ice show temperatures rising, while dust layers diminish evidence of stable, fertile conditions perfect for cultivating crops. Almost simultaneously across the globe, humans began domesticating wheat, rice, and maize. This wasn't coincidence, it was necessity. As the ice reveals, the chaotic climate of the Ice Age, with its wild swings between cold and warm, made farming impossible. Only when the planet settled into a temperate rhythm could agriculture take root, enabling villages, then cities, then empires to flourish. Yet the ice also tells darker tales of civilizations undone by climate. Take the Akkadian Empire, which ruled Mesopotamia 4,200 years ago. Just as their cuneiform tablets boast of prosperity, Greenland's ice cores record a sudden spike in dust, proof of a megadrought that stretched for centuries. Archaeological sites confirm the catastrophe: abandoned cities, layers of wind-blown silt, and skeletal remains with signs of starvation. Similar stories emerge from the Maya collapse around 900 AD, when ice from the Andes shows prolonged droughts coincided with the emptying of majestic stone cities. What makes these records so haunting is their precision. We're not guessing at causes. The ice directly links societal collapse to climate extremes, showing how even advanced cultures could crumble when the rains failed. But here's the twist: ice cores don't just reveal vulnerability, they highlight human ingenuity. During the Little Ice Age, when glaciers advanced and frosts killed crops, European societies adapted by diversifying food sources, inventing new farming tools, and expanding trade networks. The ice's chemical record of colder temperatures aligns perfectly with historical innovations, proving hardship often spurred creativity. Similarly, the Dust Bowl of the 1930s, visible in ice cores as a spike in North American dust, led to agricultural reforms that reshaped modern farming. What emerges from these frozen archives is a profound dialogue between climate and culture. The same forces that scattered our ancestors also forged resilience. The droughts that toppled empires also cleared the way for new beginnings. Ice cores remind us that humans have always been shaped by their environment, but unlike any species before us, we've also learned to shape it in return. As we face today's climate challenges, these frozen lessons offer both a warning and a beacon. The past shows us how fragile societies can be, but also how fiercely they can adapt when survival hangs in the balance. Even the most meticulously preserved ice cores hold mysteries, gaps where entire years or even centuries of climate data seem to have vanished. These missing layers, far from being mere imperfections, tell their own dramatic story. Imagine flipping through a history book only to find key chapters ripped out, their absence whispering of catastrophic events that melted or scoured away the ice. In Greenland, for instance, certain cores show sudden jumps where hundreds of years' worth of snowfall simply disappeared. At first glance, this seems like a scientist's nightmare. How can we reconstruct Earth's past with holes in the record? But these gaps are actually silent alarms, marking periods when temperatures climbed so high that surface ice melted away, erasing entire epochs in a geological heartbeat. One of the most revealing examples comes from the Eemian period. Around 120,000 years ago, the last time Earth was warmer than today. Ice cores from that era show not just thinning layers, but entire sections where the ice itself became soupy, its delicate chemical signatures blurred by meltwater. This wasn't a gentle thaw, it was a wholesale collapse of ice sheet stability under heat stress. The chilling implication: similar melt events could be in our future if warming continues unchecked. Even more telling are gaps from just 6,000 years ago, when a natural warm phase caused parts of Greenland's ice sheet to vanish entirely, proof that these frozen giants aren't as immutable as they seem. Yet these missing layers don't just warn us, they teach us. By comparing eroded sections with intact ones, scientists can pinpoint exactly which temperatures trigger irreversible melting. In Antarctica, cores reveal that once meltwater begins pooling on the surface, it accelerates ice loss by seeping through cracks and lubricating the base. This creates a feedback loop. More melting exposes darker ice, which absorbs more sunlight, which melts even more ice. The gaps in the record are like scars, marking moments when this cycle spun out of control. What makes these absences so critical is how they mirror current events. Satellite images now show the same meltwater lakes that once left voids in ancient ice cores forming atop Greenland at an alarming rate. The difference this time, past melt events unfolded over centuries, while human-driven warming is compressing those changes into decades. Those missing layers in the ice aren't just relics, they're previews. And as we drill deeper into Earth's frozen archives, we're left with a haunting question. How many more gaps will future cores contain, and what will their silence say about the choices we're making today? Some of the most ambitious ice core projects on Earth are hunting for a holy grail, a continuous slice of ice stretching back 1.5 million years. Current record holders like Antarctica's Epica core already take us an astonishing 800,000 years into the past, revealing dozens of ice ages and warm periods. But there's a critical gap scientists are desperate to fill. Around 1.2 million years ago, Earth's climate rhythm mysteriously changed. For millions of years before that, ice ages came like clockwork every 40,000 years, matching subtle wobbles in our planet's orbit. Then, suddenly, the pattern shifted. Glaciation started lasting 100,000 years instead. Why? The answer might be locked in ancient ice we haven't yet reached. Finding ice that old isn't just about breaking records, it's about cracking one of climate science's biggest unsolved puzzles. The transition from 40 to 100,000 year cycles suggests something fundamental changed in how Earth responds to orbital shifts. Some theories point to declining atmospheric carbon dioxide levels, while others suspect shifts in ocean currents or ice sheet dynamics. But without direct evidence from that era, it's like trying to solve a murder mystery without the crime scene. That's why teams are now scouring Antarctica's remotest regions, using radar to map where ancient ice might still lie undisturbed. The challenge: ice flows like slow-moving putty over millennia, so the oldest layers often get stretched, folded, or melted away. One promising target lies near Dome Sea, where the Epica core was drilled. Here, the ice sheet is over 3 kilometers thick, and mathematical models suggest its deepest layers could approach the magic 1.5 million year mark. But there's a catch. At those depths, pressure turns the lowest ice into a strange, plastic-like state where individual layers blur together. Scientists counter this by hunting for blue ice zones near mountain ranges, where ancient layers get pushed to the surface by geological forces. In 2017, researchers in the Allen Hills region found million-year-old ice this way, though in discontinuous chunks. The race is now on to find a continuous core bridging the key transition period. What makes this quest so urgent is how it parallels today's climate uncertainties. If we can understand why Earth's climate sensitivity changed in the past, why orbital wobbles suddenly triggered deeper ice ages, we might better predict how rising greenhouse gases will alter our future. Those missing millennia in the ice core record aren't just empty pages. They're the missing chapter that could explain how our planet's climate engine really works. And with drills now capable of reaching even deeper into Antarctica's frozen archives, we may soon hold ice that fell as snow when early humans were just beginning to walk upright. A time capsule waiting to reveal why the rules of Earth's climate game suddenly changed. While tree rings and ocean sediments offer valuable glimpses into Earth's past, ice cores stand apart as the gold standard for precision and detail. Think of it like comparing a blurry photograph to a high-resolution video. Other methods capture broad trends, but ice cores deliver frame-by-frame clarity, often with annual or even seasonal precision. Take tree rings, for example. A single ring might tell us whether a year was wet or dry, but it's limited to that tree's immediate environment. Ice cores, on the other hand, stitch together a planetary scale story. capturing global events like volcanic eruptions or methane surges that impacted continents simultaneously. Sediment layers from lake beds or ocean floors provide another piece of the puzzle, but they're more like a shuffled deck of cards. Layers can mix over time, blurring the timeline. Ice cores, by contrast, preserve their sequence with near-perfect fidelity. A dust band from a Saharan storm or a spike in sulfur from a volcanic blast lands in the ice and stays put, locked in place by each subsequent snowfall. This clarity allows scientists to pinpoint events with astonishing accuracy, like matching a layer of ash in Greenland's ice to the exact year a volcano erupted in Indonesia. But the real game-changer is what ice cores capture that other records can't: direct samples of ancient air. Sediments might hint at past temperatures through fossilized plankton shells, and tree rings reflect local rainfall, but neither can trap a bubble of prehistoric atmosphere. Those tiny pockets of gas in ice cores are like opening a time capsule, measuring carbon dioxide levels from the last ice age or methane concentrations during a warming spike. This direct evidence eliminates guesswork, letting researchers compare greenhouse gas levels with temperature proxies in the same ice layer, creating an airtight link between cause and effect. The true power emerges when these methods converge. By cross-referencing ice core data with tree rings, coral growth bands, and sediment layers, scientists build a multi-dimensional picture of Earth's past. For instance, a cooling event spotted in tree rings across Europe might align with a volcanic sulfate spike in Greenland's ice and a drop in ocean temperatures recorded in marine sediments. When independent records from different corners of the planet tell the same story, confidence in the findings skyrockets. This synergy doesn't just validate ice cores, it elevates all climate archives, turning scattered clues into a coherent narrative. What sets ice cores apart is their ability to resolve debates. Before ice core research, some argued that past temperature swings drove CO2 changes, not the other way around. But the ice proved otherwise, showing that CO2 consistently lagged behind temperature shifts in ancient cycles, until humans started burning fossil fuels. Now CO2 leads by a staggering margin, breaking a pattern that held for hundreds of thousands of years. No other climate record could have settled that question with such authority. Ultimately, ice cores don't replace other archives, they amplify them. Like a conductor unifying an orchestra, they harmonize disparate climate signals into a symphony of Earth's history. And as drilling techniques improve, these frozen time capsules promise even sharper insights, helping us separate natural variability from human fingerprints with ever greater precision. The next chapter of this detective story is still being written, 1 meter of ice at a time. The unshakable evidence locked in ice cores has transformed from scientific curiosity to the backbone of global climate policy. When diplomats gathered to draft the Paris Agreement in 2015, they weren't just relying on computer models or recent temperature records. They were holding centuries-old air bubbles from Antarctica, tangible proof that today's carbon dioxide levels have no natural precedent. Those frozen archives did something remarkable. They turned abstract debates about humanity's role in climate change into irrefutable fact. Before ice cores, skeptics could argue that Earth's climate had always fluctuated. But the ice silenced those doubts by revealing a pattern. Over 800,000 years, CO2 never rose above 280 parts per million without human interference. Today's levels, breaching 420 parts per million, stand as a stark anomaly in the planet's atmospheric history, a smoking gun preserved in frozen time. This data doesn't just inform policy, it dictates it. The Paris Agreement's goal of limiting warming to 1.5 degrees Celsius wasn't plucked from thin air. It was calibrated using ice core records that show how past temperature shifts of that magnitude triggered cascading effects, from ice sheet collapses to ecosystem upheavals. When nations pledge emission cuts, they're essentially trying to steer Earth back toward the stable climate bands that dominated most of the Holocene, the 10,000-year period when human civilization flourished. Ice cores define those guardrails, showing policymakers exactly how far we've strayed from the conditions that nurtured agriculture, stable coastlines, and predictable weather. But the influence goes deeper than broad targets. Ice cores help allocate responsibility among nations by revealing when the climate balance tipped. The sharp rise in greenhouse gases after 1850, visible in Antarctic ice, coincides with the Industrial Revolution, pinpointing which countries burned the most fossil fuels historically. This historical accountability shapes modern climate finance, guiding decisions about which nations should fund adaptation efforts in vulnerable regions. Similarly, the rapid methane increases captured in Greenland's ice inform global agreements to curb emissions from agriculture and landfills, proving that today's levels dwarf any natural variation. Perhaps most crucially, ice cores offer policymakers a glimpse of consequences. Layers from past warm periods like the Eemian 120,000 years ago show sea levels 6 meters higher than today, a warning for coastal cities. Dust bands from ancient megadroughts hint at future water shortages, while volcanic sulfate spikes demonstrate how quickly temperatures can drop when sunlight is blocked, informing geoengineering debates. These aren't theoretical scenarios, they're proven outcomes etched in ice, giving leaders a playbook of risks to avoid. The true power of these frozen records lies in their neutrality. Unlike economic forecasts or political agendas, ice cores present raw planetary data, unfiltered and unambiguous. When a senator questions climate science or a corporation greenwashes its emissions, ice cores cut through the noise with a clarity that transcends language and borders. They remind us that climate policy isn't about ideology. It's about aligning human activity with the Earth's own operating manual, written in layers of snow long before the first cities rose. And as drilling projects retrieve ever older ice, we're not just uncovering the past, we're drafting the future, one informed decision at a time. Even in the most pristine ice cores, drilled from the untouched glaciers of Antarctica and the remote peaks of the Himalayas, scientists are uncovering something profoundly unsettling: microscopic plastic particles. These tiny synthetic fragments, some no larger than a grain of pollen, have infiltrated ice layers dating back to the 1940s, marking the moment plastic production skyrocketed worldwide. It's a discovery that rewrites the boundaries of human impact. If microplastics have reached Earth's most isolated ice sheets, carried by winds and ocean currents, nowhere on the planet remains untouched by our pollution. The types of plastic trapped in the ice tell their own story. Some particles match fibers from synthetic clothing, likely shed during laundry cycles and swept into the atmosphere. Others resemble fragments from degraded packaging or paint chips, ground down over decades until they became small enough to ride global air currents. Most alarming are the nanoplastics particles so minuscule they can penetrate cells found even in ice cores from Greenland's deepest, oldest layers. These aren't just pollutants, they're time stamps, marking the exact era when humanity's reliance on plastic began overwhelming natural systems. What makes this contamination so unprecedented is its persistence. Unlike volcanic ash or dust, which eventually settle or dissolve, plastics resist breakdown. A single microplastic buried in ice 100 years ago will still be there today, chemically unchanged. Ice cores reveal this durability has turned Earth's frozen archives into a synthetic fossil record. Future scientists studying our era won't just find traces of climate shifts, they'll uncover layers studded with indestructible plastic, a permanent testament to the Anthropocene. The implications stretch beyond symbolism. Plastics in ice cores accelerate melting by darkening surfaces, absorbing sunlight that pristine ice would reflect. This creates a feedback loop. As more ice melts, it releases older microplastics trapped deeper within, which then spread and worsen further melting. Worse, these particles act like sponges, soaking up toxic chemicals from seawater or the atmosphere. When ingested by microorganisms at the base of polar food chains, they introduce poisons into ecosystems already stressed by warming. Yet these frozen plastic traces also offer a perverse kind of clarity. They prove that no international treaty or recycling program has yet reversed the tide of synthetic pollution. Unlike greenhouse gases, which mix invisibly into the air, microplastics in ice cores are visceral, visible under microscopes, tangible proof of a crisis woven into the fabric of the planet itself. And just as ice cores once revealed the rise of leaded gasoline or industrial soot, they now document humanity's plastic addiction with unflinching precision. The lesson buried in these contaminated layers isn't just about pollution, it's about legacy. Long after today's cities crumble, our plastics will endure, preserved in ice like artifacts of a civilization that reshaped Earth down to its atomic structure. Future generations may study these cores not to understand natural climate cycles, but to decipher how a single material came to infiltrate every corner of the globe, and why those who lived in its golden age failed to stop it. Drilling into Earth's frozen archives is no simple feat. It's a high-stakes battle against some of the harshest conditions on the planet. Imagine working in -40-degree temperatures, where metal tools shatter like glass and diesel fuel turns to jelly, while howling winds threaten to bury your equipment under mountains of snow. This is the daily reality for ice core teams, who brave the extremes of Greenland and Antarctica to retrieve cylinders of ice that hold Earth's secrets. The challenges begin long before the drill even touches the ice. Just transporting tons of equipment to remote drilling sites requires traversing crevasse-riddled glaciers in tracked vehicles, or relying on ski-equipped planes that can land on makeshift ice runways. One wrong step and entire seasons of work and millions of dollars in funding can vanish into the abyss. Then comes the drilling itself, a delicate ballet of precision and brute force. Specialized drills, some weighing over 10 tons, must carve out perfect cylindrical cores without fracturing the ice or introducing contaminants. At Antarctica's Wise Divide Camp, engineers developed a revolutionary thermal drill that melts its way down with a heated tip, leaving the surrounding ice undisturbed. But even this cutting-edge technology isn't foolproof. At depths beyond 2,000 meters, the pressure becomes so intense that boreholes can snap shut like a vise, trapping drills and crushing years of effort in an instant. Teams work around the clock in shifts, knowing that a single mechanical failure, a snapped cable, a frozen pump, could mean losing precious ice formed during the reign of the pharaohs. Contamination is the silent enemy in this frozen chess game. A single fingerprint, a drop of sweat, or a whiff of exhaust can taint ice that's remained pristine for millennia. To prevent this, drillers wear sterilized suits resembling spacesuits, handling cores with tools dipped in ultra-pure solvents. The ice itself is processed in clean rooms kept at sub-zero temperatures, where scientists in climate-controlled glove boxes slice samples with band saws cooled by liquid nitrogen. Even the air poses risks. Modern carbon dioxide can seep into ancient bubbles, so cores are vacuum sealed in aluminum tubes the moment they're extracted. At the East Greenland Ice Core project, researchers once abandoned an entire drill site after detecting trace amounts of aircraft fuel in the snow. proof of just how relentless the pursuit of purity must be. What makes these Herculean efforts worthwhile are the moments of triumph, like when the European project for ice coring in Antarctica finally punched through to ice dating back 800,000 years, revealing atmospheric details from when early humans first harnessed fire. Or when Greenland's NEEM team recovered ice from the Eemian period, capturing a snapshot of Earth's last warm era. These breakthroughs don't just happen, they're wrested from the ice by teams who endure months of isolation, physical exhaustion, and the constant threat of failure. Every meter drilled is a victory against the elements, a testament to human ingenuity in the face of a planet that guards its secrets fiercely. The legacy of these missions extends far beyond scientific journals. Each core retrieved pushes the boundaries of what we know about Earth's climate system, helping refine models that predict future changes. The same drills that once struggled through Antarctic blizzards now inspire technologies for exploring icy moons like Europa, where similar techniques might one day search for extraterrestrial life. And perhaps most importantly, these frozen time capsules remind us that understanding our planet isn't a passive exercise, it's an active struggle, demanding everything from engineering brilliance to sheer human grit. The next chapter of Earth's story won't be found lying on the surface. It's buried deep, waiting for those willing to brave the cold and bring it into the light. The clock is ticking for Earth's frozen archives as rising temperatures threaten to erase irreplaceable layers of climate history. Across Greenland, Antarctica, and alpine glaciers, ice that has preserved Earth's secrets for hundreds of thousands of years is now melting at unprecedented rate, taking with it invaluable data about past climates, ancient atmospheres, and even early human civilizations. In a race against time, scientists are launching urgent missions to extract and safeguard these cores, storing them in specialized vaults like the National Science Foundation's Ice Core facility in Colorado. This high-security freezer, kept at a constant -36 degrees Celsius, houses over 20,000 meters of ice cores, each one a fragile time capsule that might soon vanish from the wild. What makes this rescue effort so critical is the sheer irreplaceability of these frozen records. Unlike books or artifacts, which can be copied or restored, once an ancient ice layer melts, its unique chemical signatures and trapped air bubbles are lost forever. Take the Quelquea ice cap in Peru, for example. Just 2 decades ago, its cores held pristine records of tropical climate stretching back 1,800 years. Now, rapidly accelerating melt has destroyed entire sections, erasing data about El Niño patterns and pre-Columbian droughts that could have informed modern water management. Similar losses are unfolding from the Alps to the Himalayas, where glaciers that have persisted since the last ice age are retreating upslope by meters every year. The process of preserving these cores is as precise as it is urgent. After extraction, each meter-long cylinder is wrapped in sterile plastic, labeled with its exact depth and location, and shipped in refrigerated containers to facilities that mimic polar conditions. At the NSF's vault, robotic arms handle the cores to prevent contamination, slicing thin samples for analysis while the majority remains in deep storage. This isn't just about freezing ice, it's about preserving its integrity down to the molecular level. Even minor temperature fluctuations can distort gas bubbles or alter isotopic ratios, turning a priceless climate record into flawed data. But the real innovation lies in how these archives are being future-proofed. Researchers are creating digital twins of each core, using laser scanners to map their layers in micrometer detail. Advanced mass spectrometry captures their chemical profiles, while machine learning algorithms cross-reference these with global climate models. The goal: to ensure that even if the original ice is someday lost, its secrets will remain accessible for generations of scientists. Some teams are going further, burying duplicate cores in Antarctica's snowfields, nature's own freezer, where they'll theoretically survive for centuries under accumulating snowfall. This isn't just a scientific endeavor, it's an act of intergenerational responsibility. The ice cores we save today could answer questions future researchers haven't even thought to ask. They might reveal unknown climate feedback loops, help calibrate models for alien planets, or even document ancient pandemics trapped in the ice. As the planet warms and glaciers disappear, these frozen libraries become more than research tools. They're a legacy, a bridge between the Earth we've inherited and the one we're shaping for those who'll come after us. The work happening in vaults and labs right now isn't just preservation. It's the careful passing of a torch, ensuring that the stories etched in ice won't fade before we've had the chance to listen. The same drilling techniques that unlock Earth's climate secrets are now paving the way for one of humanity's most profound quests, the search for extraterrestrial life. On frozen moons like Jupiter's Europa or Saturn's Enceladus, vast oceans churn beneath miles-thick ice shells, environments eerily similar to the subglacial lakes of Antarctica, where scientists have found resilient microbes thriving in isolation for millions of years. The tools honed to extract pristine ice cores on Earth, thermal drills to prevent contamination, sterile sampling chambers, and sensors capable of detecting microscopic life are being adapted for space missions, turning planetary scientists into cosmic ice detectives. Consider Europa, where NASA's upcoming Europa Clipper mission will use radar to map the moon's icy crust, identifying thin spots where future landers might drill. The challenges mirror those faced in Greenland's hardest-to-reach ice sheets: how to retrieve samples without introducing earthly contaminants or destroying delicate organic clues. Solutions developed for Antarctic drilling, like the clean room protocols used at Lake Vostok, where Russians successfully reached a subglacial ecosystem sealed off for 15 million years, are now blueprints for sterilizing space probes. Even the way ice cores are analyzed layer by layer informs how extraterrestrial ice might be scanned for biomarkers, with spectrometers tuned to detect amino acids or lipid residues that hint at alien biology. But the parallels go deeper than technology. Ice cores have revealed how life persists in Earth's most extreme frozen environments, offering a playbook for what to seek elsewhere. In Greenland, researchers found bacteria surviving in ice dating back 120,000 years, their metabolism slowed to near stasis. On Mars, where ice caps contain layered deposits similar to Earth's glaciers, such organisms could be preserved in suspended animation. Even more tantalizing are the ice-entrapped microbes from Antarctica's blood falls, a subglacial brine rich in iron-eating bacteria that thrive without sunlight, a model for how life might exploit chemical energy on Europa's dark ocean floor. The stakes couldn't be higher. If future missions like Europa Clipper or ESA's Jupiter icy moons explore or detect even simple cellular structures, ice core science will have provided the roadmap. Techniques like laser-induced fluorescence, used to spot microbial layers in Greenlandic ice, could one day highlight alien microbes in a Europan core. And just as Earth's oldest ice captures moments when oxygen first filled our atmosphere, a signature of early photosynthesis, ice from other worlds might preserve similar tipping points in alien biospheres. What makes this crossover so revolutionary is its humility. The same drills that once sought climate data now help answer whether we're alone in the universe. Every innovation to protect ice cores from contamination doubles as a safeguard against false positives in the search for extraterrestrial life. And if one day a probe drills into Europa's crust, retrieving ice that holds the first proof of life beyond Earth, it'll stand on the shoulders of centuries of polar science where the first steps were taken not among stars, but in the silent, frozen heart of our own planet. What if you could hold a piece of Earth's climate history in your hands, not as a scientist, but as a curious citizen? That's the revolutionary idea behind projects like Ice Detective, where everyday people help decode the frozen messages locked in ice cores. This isn't just about crowdsourcing labor, it's about breaking down the ivory towers of climate science and letting the world participate in discoveries that shape our collective future. Imagine logging onto your computer and sifting through high-resolution scans of ice core layers, flagging unusual dust bands or volcanic ash streaks that might have stumped algorithms. That's exactly what thousands of volunteers are doing, turning coffee breaks into genuine scientific contributions. The beauty of these initiatives lies in their dual impact. On one hand, they accelerate research by distributing the painstaking work of analyzing ice core data across a global network of eyes. A single core can contain hundreds of thousands of layers, each requiring meticulous examination, a task too vast for any single lab. But when a teacher in Tokyo spots a sulfur spike linked to an undocumented volcanic eruption, or a student in Brazil identifies a dust layer from an ancient Sahara drought, they're adding pieces to a planetary puzzle that no professional team could complete alone. Beyond speeding up science, these projects transform passive observers into active witnesses of climate change. There's something visceral about seeing the exact moment, frozen in ice, when lead pollution spiked during the Roman Empire, or when microplastics first appeared in the 1950s. It turns abstract concepts like parts per million into tangible strips of contamination visible under a digital microscope. Participants don't just learn about climate history, they experience it layer by layer, connecting personal actions to planetary patterns in ways that graphs and articles can't replicate. The ripple effects are already visible. Ice Detective volunteers have uncovered previously overlooked climate events, like a medieval volcanic eruption that left a faint but global signature in ice cores from both hemispheres. Others have helped map the spread of industrial pollutants across continents by tracking heavy metal deposits year by year. These aren't just academic exercises, they're building a more nuanced understanding of how human activities intertwine with Earth's systems, knowledge that's now informing everything from air quality regulations to disaster preparedness. Perhaps most powerfully, citizen science bridges the gap between data and democracy. When people engage directly with evidence of rising CO2 levels or disappearing Arctic ice, they're less likely to dismiss climate science as distant or debatable. They become ambassadors for evidence-based action, armed with first-hand experience of the planet's fragile balance. And as these projects expand, with some now incorporating VR to let users walk through ice cores or AI tools that teach pattern recognition, they're proving that the next great climate discovery might not come from a research station, but from a living room halfway around the world. This collaborative approach is rewriting the rules of who gets to participate in science. No longer confined to PhDs and polar expeditions, the story of our planet's past and the power to shape its future is being placed in the hands of anyone with curiosity and an internet connection. And as more people touch, explore, and interpret these frozen archives, they're not just studying history, they're helping to write the next chapter. The next frontier of ice core research isn't just about drilling deeper, it's about seeing clearer. Cutting-edge technologies are transforming how we read these frozen archives, turning what was once painstaking manual analysis into a high-resolution window into Earth's past. Take laser ablation, for instance, where scientists once relied on laborious chemical tests to study ice layers. lasers now vaporize microscopic sections, instantly revealing their composition with precision down to parts per trillion. This isn't just faster, it's uncovering details previously invisible, like trace metals from asteroid impacts or pollutants from ancient smelting operations, all preserved in ice thinner than a human hair. Artificial intelligence is another game changer, sifting through centuries of climate data in minutes. Machine learning algorithms trained on known ice core patterns can now identify subtle correlations humans might miss, like how a volcanic eruption in Alaska triggered droughts in Africa, or how shifts in ocean currents echoed in Antarctic snowfall. At the University of Copenhagen, AI recently passed 800,000 years of ice core data in weeks, a task that would have taken decades, revealing a previously unnoticed cycle of rapid warming events tied to solar activity. These tools aren't replacing scientists, they're amplifying their vision, letting them spot planetary connections hidden in the noise, but the real excitement lies in the hunt for Earth's oldest ice. Later this decade, the European Beyond Epica mission will drill near Dome Sea in Antarctica, targeting ice up to 1.5 million years old, nearly doubling our current record. The challenges are staggering. At those depths, ice flows like molasses, distorting layers into chaotic folds. To tackle this, teams are deploying radar systems that peer through kilometers of ice, mapping hidden structures like a medical scan. The payoff could solve one of climate science's biggest mysteries: why Earth's ice age cycles suddenly shifted from 40,000 to 100,000 years around 1 million years ago. The answer might lie in greenhouse gas levels trapped in that ancient ice, offering clues about how sensitive our climate really is. Meanwhile, NASA's IceCube project is testing portable drills in Greenland that could one day explore icy moons like Europa. These prototypes use heated drill bits to melt through ice without vibration, minimizing contamination, a technique perfected in Antarctica's subglacial lakes. Back in labs, quantum sensors are being tuned to detect single molecules in ice samples, promising insights so precise they could reveal annual pollution levels from the Bronze Age or trace the rise of agriculture through pollen trapped in bubbles. What makes this technological leap so urgent is the race against time. As warming melts glaciers worldwide, these innovations let us salvage climate data before it's lost forever. But they're also rewriting textbooks in real time. Last year, a Swiss team using ultra-high-resolution imaging found microplastics in ice cores previously thought pristine, proof that even our most remote archives bear humanity's fingerprint. The future of ice core research isn't just about older ice. It's about sharper eyes, smarter tools, and a deeper understanding of how delicately our planet's systems are intertwined. And with every technological breakthrough, we're not just uncovering Earth's past, we're refining our roadmap for its future. From Hollywood blockbusters to indie video games, ice cores have transcended scientific journals to become powerful storytelling tools, turning dense climate data into gripping narratives. Their striking visual contrast, pristine white layers banded with volcanic ash or dust, makes them instantly recognizable symbols of Earth's fragile history. Take the Emmy-winning documentary Chasing Ice, where cinematographers trained their lenses on ice cores being drilled in Greenland, capturing the moment scientists gasped at a layer of soot from the Industrial Revolution. That single, smoky streak in otherwise clear ice became a visceral shorthand for human impact, translating centuries of emissions into an image anyone could understand. Video games have embraced ice cores too, weaving them into interactive storytelling. In the survival game Frostpunk, players encounter a fictional ice core revealing a past climate catastrophe, a clever narrative device that mirrors real-world science. By analyzing the virtual core, players uncover clues to survive their own frozen apocalypse, subtly learning how ice archives work. Even Civilization VI got in on the act, adding ice cores as a late-game research item that boosts environmental policy. These aren't just Easter eggs, they're stealthy science lessons, leveraging gameplay to teach players about paleoclimatology without a single textbook lecture. The arts have also found poetry in ice cores. Contemporary artists like Zaria Foreman create hyperrealistic pastel drawings of ice core cross-sections, magnifying their layers to mural-sized scales. Exhibited in galleries from New York to Tokyo, these works invite viewers to trace climatic shifts with their fingertips, transforming data into tactile beauty. Meanwhile, composers like John Luther Adams have translated ice core records into musical scores, assigning musical notes to chemical concentrations. So a spike in volcanic sulfates might trigger a crescendo of strings, making climate history audible. What makes ice cores so compelling in popular culture is their duality. They're both rigorous scientific instruments and time-traveling storytellers, bridging the gap between hard data and human emotion. When a Netflix documentary zooms in on an air bubble trapped during the Roman Empire, or a museum display lets visitors drill a simulated core, they're not just sharing facts, they're creating moments of connection. And in an era of climate anxiety, these stories matter more than ever. By framing ice cores as planetary diaries rather than abstract graphs, storytellers empower audiences to see themselves as part of Earth's ongoing saga, not just observers but characters shaping the next chapter. The true power of these cultural interpretations lies in their accessibility. A teenager playing Frostpunk or a gallery-goer mesmerized by ice core art might never read a scientific paper, but they'll walk away understanding that Earth's climate has rhythms, that humans have altered them, and that the ice remembers. In a world drowning in misinformation, these creative retellings are more than entertainment, they're lifelines, turning ancient frozen archives into allies in the fight for our future. As ice cores continue to inspire filmmakers, game designers, and artists, they're proving that science doesn't have to stay in the lab. Sometimes, the most profound truths emerge not from a microscope, but from the stories we wrap around them, stories that linger long after the credits roll or the game console powers down. And in those stories, ice cores become more than climate records. They become mirrors, reflecting back not just where we've been, but who we are. One persistent myth about climate change suggests that today's rising carbon dioxide levels are just part of Earth's natural cycle, nothing unusual compared to past fluctuations. But ice cores dismantle this argument with undeniable precision. Those frozen archives show something startling. While CO2 has indeed risen and fallen over hundreds of thousands of years, the speed and scale of the current spike have no natural parallel. Picture a graph tracing CO2 levels from an Antarctic ice core. For 800,000 years, the line dances rhythmically between 180 and 280 parts per million, like the steady pulse of a heartbeat. Then, in the last century, it rockets upward like a rogue firework, smashing through 400 parts per million and still climbing. This isn't a gentle uptick, it's a vertical leap, unparalleled in the ice core record. Some argue that past warm periods, like the Eemian interglacial 120,000 years ago, saw similar CO2 levels, but ice cores reveal a critical distinction. Those ancient peaks took millennia to develop, giving ecosystems time to adapt. Today's rise has happened roughly 100 times faster, a breakneck acceleration tied directly to fossil fuel combustion, the smoking gun, isotopic fingerprints in modern CO2. Carbon atoms from burned coal, oil, and gas carry a distinct signature. different from those released by volcanoes or oceans. Ice cores show this human-made carbon flooding the atmosphere only after the Industrial Revolution, a timeline that aligns perfectly with global energy use records. Another common misconception is that temperature changes historically drove CO2 shifts, not the other way around. It's true that ice cores show CO2 lagging behind temperature during Ice Age cycles by about 800 years as warming oceans gradually released stored gas. But that's precisely what makes today's situation so alarming. For the first time in Earth's history, CO2 is leading the charge, soaring before temperatures fully respond. It's as if someone pressed fast forward on a process that once unfolded glacially slow. Perhaps the most powerful rebuttal ice cores offer lies in their global consistency. Deniers sometimes cherry-pick data from single locations or brief time spans. But when you compare cores drilled from Greenland to Antarctica, from the Andes to the Himalayas, they all tell the same story. Current CO2 levels are higher than at any point in the last 800,000 years, and the rate of increase is off the charts. Even more telling, the ice preserves no precedent for the sudden, simultaneous rise in CO2, methane, and nitrous oxide we see today, a trio of greenhouse gases now surging in lockstep due to human activity. These frozen records do more than silence misinformation. They reframe the conversation by showing us what natural variability really looks like. Ice cores strip away excuses. There's no ancient volcano, no solar cycle, no mysterious planetary rhythm that explains the present anomaly. The truth is written in those layers, clear as ink on parchment. We are the authors of this change. And just as ice cores have chronicled our impact, they'll also document how, or if, we choose to respond. Behind every ice core discovery lies a human story, tales of perseverance, ingenuity, and moments of pure scientific exhilaration that transform frozen data into gripping narratives. Take the team at Vostok Station in Antarctica, where researchers once endured -89-degree temperatures to drill into ice older than human civilization. One scientist described the heart-stopping moment they pulled up a core section with strangely cloudy ice later, realizing they'd breached a previously unknown subglacial lake sealed for 15 million years. The lab that day erupted in shouts and hugs, not just for the discovery, but because they'd narrowly avoided contaminating one of Earth's last pristine ecosystems. Then there's the legendary volcanic layer chase of 1991, when Greenland's drill teams noticed an unusual band of ash in their cores. They worked around the clock, racing against a brewing blizzard to extract adjacent samples. Their haste paid off. Chemical analysis matched the ash to Alaska's Mount Churchill eruption 1100 years prior, revealing how a single volcanic event could alter global weather for years. One technician still recalls the surreal sight of volcanic dust swirling in their headlamps as winds howled outside, connecting them viscerally to a catastrophe witnessed by Viking settlers centuries ago. For glaciologist Zoe Thomas, her career-defining moment came not in the field but in a cramped lab. While studying a supposedly boring section of Antarctic ice, she spotted microscopic charcoal flecks others had overlooked, evidence of prehistoric megafires that rewrote our understanding of past climate feedback loops. It felt like the ice was whispering secrets, she later said, describing how those blackened particles led her team to track wildfires across 3 continents during the last interglacial period. The human drama isn't limited to breakthroughs. There's dark humor too, like the time a drill team in the Alps had to haul their malfunctioning equipment up a glacier by hand for repairs, only to discover the issue was a single frozen screw. Or the researcher who spent weeks developing a sterile sampling protocol, then accidentally sneezed on a priceless core. It became a cautionary legend taught to every new recruit. These stories matter because they remind us that science isn't just graphs and theories, it's people enduring frostbite, laughing over camp stoves, and occasionally dancing with joy when the ice finally gives up its secrets. Perhaps the most poignant tale comes from a retiring driller at Summit Station. On his last expedition, he extracted a core containing air bubbles from the year of his birth, 1952. Holding that ice, he realized his entire life's work had been preserving the very era that shaped him, creating a legacy as layered and enduring as the ice itself. Moments like these bridge the gap between data and humanity, proving that every centimeter of ice carries not just Earth's history, but our own. Want to become an ice core detective without braving sub-zero temperatures? Thanks to digital archives, the same groundbreaking data that transformed climate science is now at your fingertips. Platforms like the National Oceanic and Atmospheric Administration's Paleoclimatology database have flung open the vaults, letting anyone explore Earth's frozen history through interactive graphs, raw datasets, and even 3D core scans. Imagine tracking the exact year volcanic ash from Mount Tambora circled the globe in 1815, or watching CO2 levels climb from the last ice age to the Industrial Revolution, all with a few clicks. These digital tools don't just display numbers, they bring ice cores to life. Zoom in on high-resolution images of individual layers where volcanic sulfates appear as delicate yellow bands and dust storms leave gritty streaks. Overlay multiple cores from different continents to spot global events, like how the same sulfate spike appears simultaneously in Greenland and Antarctic ice after mega eruptions. Some platforms even let you compare ancient climate swings with historical records, revealing how a 17th century temperature dip in the ice aligns with diary entries about frozen Thames River fairs. For educators and students, these archives are gold mines. Build classroom exercises around real datasets, have students graph medieval lead pollution spikes tied to silver mining, or identify the ice age cycles hidden in oxygen isotope ratios. Amateur scientists can contribute too, joining citizen projects that classify dust particles or flag unusual layers in unprocessed core scans. There's something powerful about manipulating the same graphs that appear in IPCC reports, transforming abstract headlines into tangible evidence you've explored firsthand. Beyond research, these platforms preserve ice cores that may soon vanish. As glaciers retreat, digital backups ensure that even if original cores degrade, their data remains accessible. Future generations might study virtual cores from glaciers that no longer exist. Their meltwater long since flowed into rising seas. The true gift of these digital archives isn't just access, it's empowerment. When you toggle between pre-industrial and modern CO2 levels on an interactive graph, or trace the radioactive fallout from nuclear tests in 1960s ice, you're not just learning history. You're witnessing the planet's pulse, reading the same evidence that convinced scientists of our unprecedented impact. And in an era of climate uncertainty, that knowledge isn't just fascinating, it's foundational. Ice cores are far more than frozen water. They're Earth's silent historians, meticulously recording every gasp of volcanic ash, every whisper of ancient wind, and every fingerprint humanity has left on our planet's atmosphere. These slender cylinders of ice, painstakingly extracted from the world's most remote glaciers, have rewritten our understanding of climate, reshaped environmental policies, and even given us glimpses into civilizations long vanished. What makes them truly extraordinary isn't just their ability to preserve the past, but their power to illuminate the road ahead. When you hold a piece of ice that formed during the Roman Empire, you're not just touching history, you're holding a warning, a promise, and a challenge all at once. Consider the profound lessons encoded in these frozen archives. They've shown us that Earth's climate doesn't change gradually. It can flip between states with terrifying speed, as when Greenland's ice layers revealed temperatures spiking 10 degrees Celsius within a decade at the end of the last ice age. They've exposed how tightly intertwined our world is, where dust from the Sahara ends up in Arctic ice and pollution from 19th century factories leaves its mark in Antarctica. Most crucially, they've documented what happens when delicate balances are disrupted, whether by volcanic eruptions blocking sunlight or industrial smokestacks pumping carbon into skies. The message is unmistakable. Small shifts can cascade into planetary transformations, and we're currently engineering one of the most dramatic shifts in Earth's history. Yet ice cores also offer hope. They prove that when societies recognize environmental threats like the sudden drop in lead pollution after ancient Rome's collapse or the recovery of ozone-depleting chemicals following the Montreal Protocol change is possible. Those frozen bubbles of pre-industrial air aren't just relics. They're proof that Earth can regain equilibrium if given the chance. The technologies we've developed to study ice cores, from lasers that read isotopic ratios to AI that deciphers climate patterns, are the same tools helping us build a sustainable future. As this video ends, we're left with a simple but staggering truth. Future ice cores will record what we do next. Will they show a swift decline in carbon emissions as humanity transitions to clean energy? Or will they capture the moment we crossed irreversible thresholds, with layers of meltwater erasing the very archives that could have guided us? The answer isn't in the ice yet, it's in our hands. Share this journey through Earth's frozen memory to spread these vital lessons. Drop a comment below about which prehistoric revelation stunned you most. Was it the volcanic winter that nearly wiped out humanity, or the medieval pollution visible in alpine ice? And if you're hungry for more mysteries from the depths of time, hit subscribe, because understanding where we've been is the first step toward change.